In this video, I'm going over 9 exercises that are related to chapter 14. As you go through the video, for each exercise, you can pause the video, do the exercise on your own, and then watch my explanation and my answer to each exercise. First question, what is the mechanism and the reaction product of the following reaction? Here we have a tertiary compound that's 2-bromo, 2-methyl-butane, and reaction is with hydroxide and heat. Hydroxide would indicate that reaction mechanism is bimolecular if it's elimination reaction, because it's a strong base. If it's substitution reaction, then it has to be unimolecular reaction because substrate is tertiary. Here, important information is that reaction is carried out with heat. Heat favors elimination. So combination of the two, strong base, hydroxide, and heat, means that reaction is elimination reaction. And with tertiary substrates, E2 elimination is preferred. Tertiary substrates undergo very fast elimination reaction, much faster than secondary or primary. So correct answer is C, that reaction mechanism is E2, and then you have the product 2-methyl-2-butene. Next question, which of the following transition states results in formation of a cis alkene? So there are 4 possible transition states. And first one, transition state A, we can see on vertical bonds, bromine and hydrogen are antiperiplanar to each other. So elimination of those 2 substituents will result in formation of a double bond. 2 substituents, alkyl substituents, methyl and ethyl group, methyl group on carbon closer to us and ethyl on one further away, are on the opposite sides of bond that is going to be formed. Double bond is going to be formed, which means that this product is going to be trans. And so transition state A results in trans alkene. B actually cannot undergo elimination. So conformation B has carbon-carbon bond antiperiplanar to carbon-bromine. That means that elimination reaction is not possible from this conformation because we need carbon-hydrogen bond to be antiperiplanar to carbon-bromine. C, we have eclipsed conformation. Now, carbon-hydrogen is eclipsing with carbon-bromine. In theory, elimination from this conformation is possible, but this is high energy conformation, and in turn that means high energy transition state. So this is not a reasonable transition state because its energy is too high because of the eclipsing interactions. And so even though this would result hypothetically in elimination reaction, this is not a reasonable transition state. That happens in some cyclic systems, but even then it's rare. So C is also not correct answer. And in transition state D, we have carbon-hydrogen and carbon-bromine bonds being antiperiplanar to each other. So elimination of those 2 groups will result in formation of pi bond. And we can see that methyl and ethyl groups are on the same side. That means they will also end up being on the same side of newly formed double bond. So that's going to be cis alkene. So correct answer is D. Next questions. We have several reactions, and for each reaction we should indicate reaction mechanism. So first one, we have iodocyclohexane, and reaction is in methanol. So methanol acts either as a base or as a nucleophile. It's weak base or weak nucleophile. Since starting material is secondary, then reaction mechanism depends on the nature of the base or the nucleophile. Weak base, weak nucleophile is going to favor unimolecular reaction. So reaction is going to be either SN1 or E1. Since reaction is carried out with heat, that favors elimination, and that means that reaction mechanism is E1. Question number 4. Again, we have secondary substrate, 3-bromopentane, and now we have strong base, strong nucleophile, sodium alkoxide, sodium methoxide in this case. That means that reaction mechanism is bimolecular, SN2 or E2. Reaction temperature is what we consider to be a low reaction temperature, 25 degrees Celsius or room temperature. That favors substitution. So reaction mechanism is going to be SN2. And the final example has fluorocyclohexane. Alkyl fluorides undergo only one possible reaction. You don't need to look at reaction conditions, and you don't need to look at nature of the base or nucleophile, or actually base, although we need to use a strong base. The only possible reaction of alkyl fluorides is E2 elimination reaction. That's because fluoride anion is poor leaving group and it can only undergo elimination reactions. Question number 6. What is the structure of the product of the following reaction sequence? And now we have sequence of 3 reactions. First reaction is reaction of 1,1-dibromo 4-methylpentane with 2 equivalents of sodium amide. So that's elimination reaction, and we are using 2 equivalents of very strong base, sodium amide. That means 2 molecules of HBr are going to be eliminated, and that means that product is corresponding alkyne, terminal alkyne. So 4-methyl-1-pentyne. Then reaction of terminal alkyne with another strong base, sodium hydride, will result in deprotonation of terminal alkyne, in formation of acetylide anion. And then we have sodium acetylide, which is strong nucleophile, and in the final 3rd step, it acts as a nucleophile in SN2 reaction with bromoethane to give the final product. And so here we have the final product. It is 6-methyl-3-heptine. So 6-methyl-3-heptine. Question number 7. What is the major or the only product of the following reaction? Here we have a cyclohexane ring with 2 substituents, with bromine and ethyl group. So it's 1-bromo-2-ethyl cyclohexane and it's trans isomer. So elimination with potassium tertiary butoxide. What is going to be the product? We know it's elimination because reaction is carried out with heat, and also tertiary butoxide is strong base and it's non-nucleophilic base. It doesn't act as a nucleophile. So it has to be elimination reaction. These conditions, strong base, favor E2 elimination conditions. In E2 elimination from small rings such as cyclopentane and cyclohexane, the 2 groups that are eliminated have to be trans to each other. Simply that's because of the reaction mechanism. So when we consider which groups are trans to bromine, because we know bromine eliminates, we can see that ethyl group is trans. So double bond cannot form towards the ethyl group because the group that would eliminate hydrogen is cis on the same side as bromine. The only way for double bond to form is away from ethyl group because that's where we have available trans hydrogen. So these are 2 groups that can eliminate. And so this is the product, 3-ethyl cyclohexane. Question number 8. What is the product of the following reaction? So now we have 2-bromo 3,3-dimethylpentane. And reaction is in ethanol with heat. Ethanol is weak nucleophile, weak base. Heat, that means elimination. So first step is going to be, since it's unimolecular reaction, loss of the leaving group, bromide anion, and that gives secondary carbocation. Secondary carbocations, as you know, are unstable and undergo rearrangements whenever possible to rearrange into tertiary carbocations. In this case, methyl group will shift, the smallest group shifts, and we end up with corresponding tertiary carbocation. Now, loss of proton from a tertiary carbocation, so base removes proton from tertiary carbocation, gives the most stable, the most substitute alkene. That's 2,3-dimethyl 2-pentene. And finally, question 9. What is the product of the following sequence of reactions? So again, elimination reaction from cyclohexane ring. In this case, since we have 1,1-dimethyl, sorry, let me go again with the name. It's 2-bromo, 1,1-dimethyl cyclohexane. So 2-bromo, 1,1-dimethyl cyclohexane. Elimination with sodium methoxide will result in formation of only one possible double bond, and that's away from 2 methyl groups, because elimination cannot involve a methyl group. It has to be hydrogen that eliminates with bromine, and only 2 hydrogens on carbon atom 3 of the original cyclohexane ring can eliminate. Only one of them eliminates, one that is trans to bromine. So that's product of the first reaction, 3,3-dimethyl cyclohexene. And the second step is addition of bromine across a double bond. So we end up with this product, 1,2-dibromo, 3,3-dimethyl cyclohexane. So this completes exercises on chapter 14.